Hello, geometry students, and welcome to the lesson on the exterior angles inequality theorem. And before we get to the theorem itself, let's discuss a little bit about what are exterior angles and interior angles. So by our definition here, it says when the sides of a polygon are extended, other angles are formed. Okay, so let's say I had a triangle. Oops. Okay. So if I extend one, so I'll name these angles here, 1, 2, 3. Okay. And if I extend one of the sides, so let's say I pick this side and I extend it a little bit, you can see that there's another angle that is formed here, and we can call that angle 4. The original angles are interior angles, and the other angles are exterior angles. So you have interior angles, that's these ones right here, angle 1, 2, and 3. And then the exterior ones are, well, there's more than one, but it's this one right here. Okay, that's the exterior angles right there. Okay. In other words, the interior angles are inside of the triangle, and then the exterior stuff is on the outside of it. Do a better job here. Okay. All right. So we can say that angle 1, angle 2, angle 3 are interior, and that angle 4 is the exterior angle. And we don't have to extend this side, we could also extend another side. So if I pick this side here to extend, if I pull this down here, well, then I have another angle here. This is angle 5, okay? And that is also exterior. So there you have it, just a very basic definition. Okay. So now let's go on to our first major theorem that we're going to prove, the exterior angle inequality theorem. It says the measure of an exterior angle of a triangle is greater than each of the two non-adjacent triangles. So let's see what this means. Okay, so I've labeled this new triangle here with all these angles, and you can see that angle 2, 3, and 4 are interior. And angle 1 is the exterior. And what this says is the measure of the exterior, so the measure of the exterior, so that's angle 1 right here. Okay, that's the exterior, is greater than the two non-adjacent. And remember, non-adjacent means it's not touching. So non-adjacent means that it's angle 3 and angle 4. Angle 2 is adjacent because it's touching angle 1. So this theorem actually says two different things. The first part of the theorem says that the measure of angle 1 is greater than the measure of angle 3. Okay. And the second part says that the measure of angle 1 is greater than the measure of angle 4. So 1 is greater than 3, and 1 is also greater than 4. Okay. And let's go forward and try to prove this. And this is a proof that is unlike any other we've seen before, because we haven't done anything with inequalities yet. We've proved things are equal, but we haven't proven anything that is unequal yet. So this is a little bit new. Okay, so the first thing that I'm going to do here is I'm going to label the midpoint of BC. So this line segment BC, it's a line segment. Okay. This is a line segment, and it's got to have a midpoint somewhere. Okay. And I don't know exactly where it is, but let's say that I found it, and I'm going to label it M. Okay. So label it M. Okay. Now, since we've labeled it M, we can see that BM and CM are congruent because M is the midpoint. So, but we'll get back to that in a minute. Next, we are going to connect A and M. Okay? And this is known as the ruler postulate. It's also called Euclid's first postulate. Okay, so I like to name things based on Euclid, especially his 5 original postulates, sort of as an honorary thing. And then we are going to extend and double the length of AM. Okay. So whatever this length was before, whatever this length was, I'm not sure what it is, but I'm going to double it out to here. And I'm going to label this point R. So one thing that we can say right off the bat is that AM and RM are congruent because we're doubling this length. Okay. But let's, I'm getting a little bit ahead of myself. You're getting way too excited. So let's explain this a little bit. I can extend and double this because this is also one of Euclid's postulates. This is Euclid's second postulate, which says that I can extend a line segment as far as I need to. Okay. We also know it sometimes as the ruler postulate. Okay. And then we are going to connect R and C. Now, if you notice in this picture, we have to be careful that angle 1 is the entire angle, is the whole thing in here, okay? It was there before and it's still the same, even if we've drawn a line through it. It hasn't changed. So connecting R and C, well, that is Euclid's first postulate. Now I am going to make a note here. We are going to show that triangle ABM is congruent to triangle CRM. Okay? So basically, these two triangles that I am about to color here, we are going to try and show that they are in fact congruent. So this triangle here and this triangle here, we're going to try and show that these two are in fact congruent. Okay. And it shouldn't be too difficult to show because we have a lot of information in here already. So the first thing we know is step 5. We know that AM, oh, I accidentally wrote MA, so we'll just go with that. MA is congruent to MB because this is by construction. In step 3. Okay. Then we also know that BM is congruent to MC or CM. Okay. So BM is congruent to CM because of the definition of midpoint. The step 1 here, the definition of midpoint. So we can say that M is the midpoint of BC. Okay. And then finally, we need an angle. So we have 2 sides here, and we need 1 angle. Well, it just so happens that we have a set of vertical angles here. Right there. Okay. So we can say that angle BMA is congruent to angle CMR because they are vertical angles. And now this proof is sort of coming together now. We can say a few more things here. And notice, again, let's not lose sight of the fact that we're trying to prove that a statement is something is bigger than something else. Okay. So let me point out this little angle right here, and we'll call that angle number 5. Angle 5. That's the little one in there. One thing that we can say about that is that the angle 5. Oh, I'm sorry. Before we say that, these two triangles are congruent. Let me not get too ahead of myself. So we can say that triangle ABM is congruent to triangle CRM by side angle side. And then I can say that angle 3, that's this one up here, is congruent to angle 5 by corresponding parts of congruent triangles. So since the triangles are congruent, then the parts of them must be congruent as well. Okay? And I'm running a little bit low on space here, so I'm going to finish my proof over here. And I want to separate that from there. Well, angle 5, you see in this picture, it's inside of angle 1. So angle 5 must be smaller than angle 1. So in step 10, I can say that the measure of angle 1, measure of angle 1, is greater than the measure of angle 5, okay, because angle 1 contains angle 5. 5 is inside of 1, so 1 must be bigger. And then finally, we can make a substitution. Since 3 and 5 are the same thing, I can take 3 and substitute it in here. So step 11, measure of angle 1 is greater than, and I'm going to use parentheses here to make a substitution, the measure of angle 3. Okay, and this is, again, a substitution using step 9. And now the proof is complete. So part 1 is done. Okay. So part 1 is entirely complete. Okay. So I've proven this part right here. That's done. Now I just want to point out here what the main technique is, because so often we need to focus on the technique as much as the actual proof itself. The idea here is, first of all, we get to build some triangles. That's something we haven't done before, using the ruler postulate, Euclid's other postulates, to build some triangles. And then we want to use CPCT, okay, to get congruent angles, and then use the fact that one angle is bigger than another because one of the angles is inside the other one. Okay? And so once again, these are big ideas that we haven't done before. Okay? But it's good to see this. Okay, so now I'm going to end this video and then continue this in the next video, where we discuss how to prove that angle 4 is smaller than angle 1.